Hey, I'm Professor Snell. I'm teaching Environmental Systems 1 this semester, and I decided I would make this video for my section, and then I'll offer it up to other professors in case they want to use it also. I'm going to do several things here. It's going to be a little bombastic. It may be kind of long um, because I want to first off show everybody how to do a thermal analysis simulation in Climate Studio. And then I want to go back and that's a bunch of stuff right there, by the way. And then I want to go back and just talk about the semester through the lens of Climate Studio and sort of remind us what we're doing with a sample model that I've quickly put together here. Anyway, let's start with thermal analysis. And so where we are is that we've spent a bunch of weeks talking about what I call the site. Well, so this semester is about passive design. There are two types of passive systems that we've discussed. One is what I call the site resource, and that's essentially sun and wind. If we just want to get really simplistic about it, sun having two components, radiation and illumination, and then wind is wind. And there's a bunch of other stuff that we've talked about, but that's the basic stuff we're modeling. And so you've configured to various degrees. If all sections are like mine, there's people at very different stages of working on this. But everybody has at least played around with or started designing a project in two climates with form being created by how the site resource is managed. And we've been doing that through using Climate Studio. And then last week or the week before, I can't remember, we started talking about the second set of systems or really grouping of systems in passive design, and that's the building envelope. And so I'm going to show you today is how to model the building envelope very basically in Climate Studio. This is a deep well here. This program can be used in a fairly sophisticated fashion by engineers. We're just architects trying to get started on this, right? So you can go as deep as you want to. I'll stay somewhere on the surface. Remember that this just in life, you should be playful, but definitely here you need to combine a rigorous approach. This is data, this is exact, or it's a simulation, so it's completely wrong always, but it's also exact in terms of we're getting data we're getting quantities that we can compare. So we need to respect that and be meticulous, but we also want to be playful and iterate. The whole advantage of Climate Studio is that or one big advantage is that it's very easy to use and to iterate. You don't know this because you haven't used many simulation tools, probably building simulation tools, but the fact that we have this interface over here where we can choose a variety of simulations and just click on them and push a couple of buttons and have a whole new simulation is fairly unique in my experience. And for people that are just learning about this, it's incredibly useful because you can quickly experiment and say, well, I wonder what would happen if I change this. I think this should happen. Is that what happens? Oh, it didn't. Why not? Let me go try to figure that out. That's the process you should go through. And you should have tons and tons of simulations that you do as you're running through this. You need to be organized. You can have a period where you're just playing around and you don't try to be organized and you just learn things with each simulation and then you sort of get lost and don't really remember what all the simulations mean anymore. But eventually you want to really label them and keep track of what you're simulating so that you know what you're comparing. Um, I know in my section, I feel like a lot of people are just kind of doing it once to get the assignment done, and that's just completely missing the point. So anyway, that's my pep talk. All right, so let's just first off, I've created obviously very simple model here. It's a single room with a window, a little small building. The way the thermal analysis tool works in Climate Studio is you first create zones. So this will be a single zone. I have a a zone layer, a window layer, and a boundary layer. I'll show you what that's for in a second. Um, so I'm going to select this zone. I'm in the CS Workflows tab, then we have this Simulations tab, um, or the Results tab, as you know. So I'm going to select my zone. I could either do it like I did there, or I could, of course, come up here and say select objects in this layer. And then I'm going to click on this zone box here. And then you get these, there's a huge number of templates in here. I think you can pick whatever you want, but for the size that project that we're doing in this class, a 600 to 800 square foot building, I'm calling it housing. I'll change this in a second. I'm going to click residential. The program name is multifamily housing. And now I have a zone over here that I can edit. So if I select this, I'm going to go ahead just before I forget. I'm going to change this to single family home, and I'll show you in a minute what that, if I remember. Again, there's so many variables in here, I'm not going to even begin to touch on them. So I'm just trying to show you a workflow and get you started. And you really should be asking yourself, like, what does this lighting thing down here do? What's dimming type, and go look at there's a decent, if you go to Climate Studio, let me pull that up. I've shared this before. It's in the document that I created and gave to everybody at the beginning of the semester about the modeling programs. But let's see, ClimateStudioDocs.com. Um, this is their basic uh, documentation website. It's very, very simple and really well laid out. But there's more information here that's not in these links, so you can also just do web searches, and you'll sometimes find pages that are also on this website that don't show up in the hot links there. Okay, anyway, and I'm going to change this name of this zone, just test. Let's say, oops, I didn't really want to close that. Okay, the first thing you should notice while we're in here is that there are these four tabs here, and let's just kind of go through them quickly. Again, you're going to need to delve into them deeper. The Loads tab is setting up the type of project, the number of people. We can change the metabolic rate, all sorts of very basic very detailed um, uh, variables that have to do with the loads that are being generated in the building or by the building's place on the site or by equipment and people inside generating heat, whatever. So that's one section, one tab that's very deep that you can play around with, and that when we chose single family home in this residential template, there's hundreds of presets now that have been chosen. So we can run a model right now. I could go out of here and run a model, and we would get results that were meaningful. Maybe not to us because we wouldn't know what all the presets were. I'm going to skip over conditioning and go to envelope. This is what we're mainly dealing with. This is the passive design uh, system that we're learning about now in class. And you can see that there's uh, that construction is divided into different types, systems basically, and we can adjust their configurations and therefore their performance um, in resistance to heat flow, and generate different outputs, which is really the goal here. What we're trying to do, and I don't think I said this, is that the way I presented it is that we start by trying to manipulate, I guess, or manage our site resource so that we get the smallest, that we move as many hours from the outside um, climate into the comfort zone inside our building, just by how we place the building and things like shading and natural ventilation and placing mass in front of southern facing glass, that kind of thing. And then once we've exhausted that very intricate and fun process, then we can fix a lot of problems, or we can tweak our design with the envelope. And so that's the way I'm looking at this, is that we have eventually how you're going to use this is you're going to have a completed design for both of your climates, and then you'll come in and define an envelope, because the envelope form doesn't need to change the form of the building. We're talking about changing the assembly the assemblies for wall systems, windows, um, some shading, tweaking perhaps, and changing the type of glazing we use. And then we can also do a lot with mechanical systems, which is not really which is not at all the topic of this semester, but something we can talk about next semester. Anyway, so here we have um, pretty straightforward. We talked last week about envelope structure and control layers. This is where these would be configured. We can add internal mass down here if we want to, and then we have an infiltration rate, which is ACH means air changes per hour, and this is probably at 50 pascals. Um, anyway, I talked about that briefly in my class. You should ask if you have questions about it. And we can either turn this on or off. If you turn it off, you're going to have zero infiltration, which is crazy, impossible to do. So anyway, the preset's zero point 0.5, which is very low, at least in the U.S. Construction. Um, in the building in Manhattan that we're in, I bet that building has an ACH of 10 at 50 pascals, probably 10.0 or 12 maybe, might be a little less. I doubt it. Definitely the building in Old Westbury is something similar, I would imagine. So they're very leaky buildings. Anyway, okay, so that's our envelope, and then the conditioning tab is mechanical systems. So I may talk about that a little bit, but we're not really dealing with that this semester. And then settings. This is dealing with your sources of fuel. And I'm not going to talk about that right now. We should talk about it, but we have weeks left, and we don't. This doesn't really affect our model. Um, we can change these at any point and change the outputs there. So that's a pretty straightforward process. So okay, so now we have this envelope defined. We just kept the defaults that came with this template, and so I won't even go in and look at what these are. And but there are defaults for all the assemblies, which aren't that many right now. If I open up the zone, and we can rename these if we wanted to, but probably doesn't make sense. If you have multiple zones, I would probably name them so you know where they are. But then what the each face gets so the exterior wall faces are split out, uh, and windows are split out. Though I'm surprised that put that in because I had not defined it yet. Maybe this was a model I'd used before. So actually, I'm going to delete that right now. Okay, so we can add that because right now that window is not there. And by the way this works in it should have turned off. Let's see if I go to no. Let me just make sure it's here. Yeah, I'm going to go and delete this curve. I don't need that. So now my window, yeah, so the window is not cut out of the zone. It's just, it has to be coplanar. And these are just surfaces. If you have a model that has wall thickness, that's fine, but you need to define just the surfaces that are touching either the outside air or are adiabatic, which would mean that they're touching something else like another building, and you're going to assume that they have no heat loss through them. That's what adiabatic means, or they are the ground. And again, I'm already taking longer than I wanted to, so I'm not sure how much I'll talk about the ground, but I am going to define it here as a boundary. Anyway, so this window is just a surface on top of that wall surface, and it has not been defined yet in this model. I'm also going to define. I'm going to turn on this boundary here. I think that. Wait, let me. Actually, I paused for a second because I had not done this in this model yet, so I'll just do it now. live. I'm going to create a surface on the floor of this building, and I'm going to put this on my boundary um, layer. And so now that is, and I'm going to choose that, and I'm going to define that as ground. See here, this ground tab. And what that, let's just talk about that for a second. So now I have ground, but you'll see what it did is it created this adiabatic boundaries layer, and then it created a ground boundaries layer and a ground boundaries zone, basically, or a object in the model. So, and this, I guess, is one thing I want to say is that if you go and look at the documentation for Climate Studio, there's different, they're always updating it. And so this is a little bit funky right now. We can't really edit these like it shows in the documentation, but this preset here, we can edit in um, somewhere. I'm not sure I even really remember where it is. There's a place we can, oh, here. We're going to keep this, our ground, as ground temperature. And what that's doing is the portion of the building that's touching the ground, which we just defined with that surface, they're pulling the ground temperature from the climate data, or climate data set that we're using, that you're using for your two climates. And so that, based on where you are in the world, it's going to change how you would want to strategize the portion of the building that's touching the ground. Anyway, so we have a ground and we have a zone. Oops. And then we could, let's just quickly run a model. I hit play. There's actually over here, there's a DOS window. I have two screens open. And you see that we got results here. Um, I'll talk about all these things in a second. Let's just go back and add a window. All I wanted to do here really was just show you. So now I'm back in the workflow. I'm going to turn on this window and select it and add it as a window here. So this is, where we're adding everything in our model. Select that. I'm going to, it's defining the default glazing, which is actually single glazed. So if you click on these things, there's lots of options. And again, this is where you're going to glaze over, but you should talk to your professor. And this is a really good opportunity to be learning about glass. We have, for example, the U value, and this is in IP units. So it's the reciprocal of the R value. In this case, it's going to be about the same. So it's going to be R1, which is really low, right? I mean, hopefully you realize that even like just a little stick frame wall might have R10, even with all the thermal bridging, or R12. So the window here has a very low R value. This SHGC means solar heat gain coefficient, and it's always a ratio. So zero point 0.9 means that 90% of the solar heat that hits this window will go through it, will not be blocked. And then TVis is the visible transmittance, and so 90% of the visible um, portion of the electromagnetic spectrum of the sun will go through this glass. So the advantage of single pane glass like this is it's very transparent both to heat and light, but it's also it lets it back out. So it's usually not very efficient as far as a full building design, and it's not the code anymore to use single pane glass, um, at least not in any building that I'm aware of, any building type. Okay, so now we have a window. We can deal with shading. We could turn the frames on and off. That's something we could talk about because the frames are going to have a different resistance to heat flow than the glass. But now we basically, and then so we could, what else could we do over here? We could add some shading. So if you had shading in your design, you could add it here and make it part of the model. And that's really all the things we need to add here: zones, windows. Or if you have interior windows, you could add those here. Um, uh, Shading of some kind, and then the ground. And then you hit run, and that's it. And a DOS window runs like that, and you get an output. Um, Let me now go. So that's how you run a thermal model. I talked about it much longer probably than I needed to because it's very straightforward. Let's look at this little model it's the same model obviously, but that I ran some quick simulations, and I thought this would be a good way of talking about kind of the point here. So first I ran, um, I set my envelope to be what they call defaults. So let me go and if I come in here to my zones. By the way, if you have multiple zones, you can select all of them together and edit them all at once, which is very helpful. Um, so their defaults, these have changed now because it's saved what I did from the very last thing that I did, not what I did the first time. But I just want to show you that if you go in here, let's say I'm going to select a roof. There's a default construction which is basically concrete, um, and so it's very very energy inefficient, though it's not unreasonable. There's a lot of buildings like this in New York City, and you may live in one. I essentially do. I live in an old brick building that has no insulation at all, um, and single pane. Well, no, we now have double pane windows here because they were replaced. But anyway, so this default setting that I ran is not that out of by any means out of the possibilities of what you might run up against. So let's look at I set for the first model, I set, um, and here, this is a good example of how you need to name these things. And it's a good idea to take screenshots. So let's say you had, and I'll show you in a minute, a much more complicated if I took a screenshot of this, at least I'd have some idea what my settings were. There's some things that aren't here, but you need to get a workflow where you're keeping track of these things, or they're really basically useless if you don't know what it is what this run was, then it's just pointless. Um, but let's then now talk about these outputs here, or these values. So first, let's start over here on the right. The 58 baseline EUI. What is EUI? That's energy utilization intensity or use intensity. I think it's utilization. It basically it's a way of comparing build, buildings of the same size to each other. So it's the energy use it's kilobTUs per square foot and square foot of floor space of usable space. So the energy use intensity, then if you're designing a house or you're designing, then you look for buildings that are similar, and what is the typical the baseline for that building type. And so here we're saying it's 58 EUI per square foot. I'm not sure. I could look it up. I'm sure it says somewhere. I don't know what if this is code in their minds, or where they're getting this baseline from. It might be from lead or something. Uh, and by the way, if we go back to all of these, so this company is a bunch of cool eggheads from MIT, and they're all Europeans as far as I can tell. So most of this stuff is really European slanted. So if I edit this, and we come in and look at these different, first of all, they're in, I should change this. I think, well, actually, even if I change to IP units, it doesn't change the values, for their wall systems. Um, but the point is, if you look through these, and if you know anything about building envelopes, these are not, sand lime brick is not something we use a lot of in the United States. Um, so these are European envelopes. The way I've been using them is just, well, it doesn't really matter. I can see there are values, and this is just for comparison purposes and to learn this semester, so it's not that big a deal, but just letting you know that if you're confused by what you're looking at, talk to us and we can help you decipher it, but it's not going to be a wood stick frame with fiberglass insulation or something like that. Okay, anyway, I go back to my run here. So we can see that we're not saving anything uh, versus the baseline because our site EUI is 335 kilobTUs per square foot. So we're way above the baseline. And what are these numbers here? Let's just skip them for now. These are this is operational carbon, very, very important to me. This is a big part of my research area. and it should be important to you. This is about climate change, but it's not. These are outputs that come from our envelope choices, so changing them won't change our envelope. So let's not talk about it right now. So really what we're looking at here is this site EUI, which is displayed in this graph. And if you look down here, though, then we have each of these um, colors relates to a specific gradation or variable. So we have equipment, fans, light, hot water, heat, and cool. We can change it from energy use intensity to energy use, so that's not per square foot. We can look at energy flows. This is a really good way of doing it because now we've got infiltration in our envelope in here and the windows. So we can, as we're developing our envelope, we can come here and look at this chart and see what's changing in a very clear way. We also have this cool thing that's zone temperature curves, that if you had multiple zones, you would be able to see in each zone how many hours the in that zone the temperature is in or out is out of the comfort zone. And there's a bunch of other cool stuff that you should play around with that I'm not going to talk about right now. So just realize, again, this is something where you should uh, have a cup of coffee or whatever it is you like to drink and have some fun, spend some time with this because there's lots of cool stuff in here, and um, it's only going to be valuable to you if you take it slowly and try to learn rather than quickly just frantically make some simulations and throw them down on the graphics down on a page. That's a terrible way of doing this. Okay, anyway, so let's go back to this energy flows. So what was my envelope? So here's my little code here. Envelope default. So that was those, and what those basically were concrete for the roof and the walls and the ground. Air changes per hour is 10, which I said is not would be typical for that default envelope. And then my window has a U value of 1. So that's what my little code there is. And you can see we got this pretty bad envelope at this point. And then all I did was I just went in and changed things one at a time. So in my next run, I changed the roof to US code, and you can see we went from 335 to 300. And by US code, I mean I just picked a roof that had an R value that was similar to what I know to be residential code in this area. Let me show you that, I guess. If I go to my, um, so I think I chose, yeah, this R27, about R28 for a roof. That's not very good, but it's very typical, I think, I think code might be 30 in our climate zone right now. I'm not sure. I'd have to look it up, and you should look it up definitely. I haven't looked at it recently. So the point is, I did a simulation. I did a quick series of simulations where I'm changing one variable. So here I changed. We're at the default. Here I changed to just made a roof that's about at US code level, and you can see that my envelope. Okay, what are we looking at here? We're looking at heat gain at the top, heat loss at the bottom. So our windows right now are actually doing what they're doing. So we're only gaining heat from our windows. We're not losing any, which I'm kind of surprised by. Actually, no, there is some small amount down here, but since these other losses are so huge, you really can't see it. I should say this too. I'm not vouching for I'm not assuming that we're going to come up with even accurate models. What we're doing is trying to understand what happens when we change variables. And if it's not doing what we think it should do, we should try to figure out why it isn't. Um, but the idea is to learn. Not We're not at the level where we're trying to create something that we would then use as part of a design and act upon. Okay. Anyway, so then the next thing I did was um, I kept the same roof, and then I changed the wall to US code, and now we're slowly inching up here. Um, Then I put in a window that's to US code, which is just basically a double pane window. That helped a little bit. Then I switched and again, you can just see what's happening. Basically, the envelopes are they're losing less. That's the green. The windows are slightly changing. Everything else is staying pretty much similar. Then I changed the ACH, the air changes per hour, and that's air leakage. so its air changes through holes in the envelope from 10 to 5, and you'll see we got a pretty big jump there in our site EUI. So in this model, air change, the air tightness is huge, and as it should be. Then what I did is I went to so the pH is for Passive House, which is sort of the gold standard for envelope design right now in the world, or at least it's pretty good. And so there's a certain level of insulation, air tightness, window performance. So I did all of those at once. I brought us to an envelope that has a passive house level of performance, including the windows, and I changed the ACH to zero point 0.5 instead of 5, which is about what it would be for passive house. And you see then we jump very to far below our baseline. We're saving 42% of energy relative to the baseline. We're at 34 EUI. And now we're starting to get a lot more gradation here that we can see, because we don't have these ridiculous numbers that are so like our air leakage here is so high, which is this light blue, that we can't even really get much of a pixelation or resolution on the rest of these variables. And here we're like, what could we work on here? We're probably not going to get the envelope any better, so this green stuff's going to stay where it is. And by the way, you notice, these ranges are changing. So when we were back here, this little line was up to, like, it looks like about 4,000. So we were losing 4,000 kilobtu's in January from the envelope, and then here it's more like 2,700. So it's much less, even though it's a much bigger bar, right? It's because the scale is changing. This is great because we're gaining a lot. So the orange is our windows. So we're gaining a lot more heat in the winter, and we're barely losing any through our windows. That's what we want, and that's because this is a south-facing window. So it's ideal for this purpose. It's a really high-performance window. We should even go look at. I'll show you in a second the magic of that window. But we could maybe try to. So here in June and July, we're gaining heat through those windows, and we don't want to be. We want to be loose. We want to be having, well, I guess we'd rather lose heat through the windows, but we wouldn't be. We're not actually losing heat here. We're losing the cooling that we've created inside is being lost through the window. So we may be able to fix this. So this may not be solar heat gain. It may be lost through interior. We're at 68 degrees inside, and it's 90 degrees outside, so that'd be a loss. But that's an area we might be able to tweak and try to do some overhangs or mess with the glass. The final thing I did, and let me see if I've got this open here. Let's go back and remind ourselves of Climate Consultant. This is for Phoenix, so it doesn't matter. I'm not going to change it right now. But remember, the whole idea here, this is a little bit of a confusing chart, but is that we're trying to get as many of these dots into the blue area as we can, because the blue area is the comfort zone. We want to do that as much with passive measures as we can, because passive measures don't require fuel, and they also allow us to have fresh air, and in other ways can be healthier. So in this chart right here for Phoenix, and these are just the strategies that Climate Consultant is saying are the best. I'm not going to get into talking about that again, but we'll notice that, so that's 1 through 14 are the passive ones, and then number 15 and 16 are cooling and heating. So that's the mechanical portion of, in Climate Consultant, you'll pretty much always get to 100% because they find passive strategies and they make the rest up with cooling and heating. So that's what we can do over here. And again, we're not doing it this semester, but I'll just show you. I went in and then just tweaked everything in the mechanical system to make it a passive house mechanical system. And I went, I might have gone overboard, but that did a drastic number on our site EUI. We now are at 11 compared to 58 for the baseline. We're saving 80% on code or whatever the baseline is here. I think this is actually below code because our other, and remember we were at 335 for a building that I probably live in right now. So this is a massive improvement. And now the point is that we really are freed up because with this little bit of energy that we require, we can we have a lot more options. Like we could definitely look at producing most or all of that requirement on the roof of this building with photovoltaics. Hopefully, we could actually produce more and make up for some of our operational carbon. Anyway, so we did a great job here. Um, so what's next? Yeah, maybe I'll just spend a few seconds talking about these different. Um, so why are people down here? People create heat. So people, this is the red. People will always be in a red or in this type of graph or for in this program will always be a red band here in the heat gain portion, and if you'll see that it should be so tiny that we can't see. Let's get to something that's a little more. I mean, the point is, I imagine that's a constant. It's just we can't even see it here because it's so tiny compared to the energy load of a really leaky building or really poor envelope building. But we get down to passive house level, and it becomes a considerable part of our heating and or of our cooling load. Um, I was used to design passive houses for a living, and we designed buildings that could be heated by the people in the house. If you had a party on the coldest day of the year, you had 15 people over, you could heat your house with just the heat of the people. So it becomes more significant as we get more energy efficient. Um, we can see, let's see, the light, again, it's kind of hard to tell. Um, but yeah, so it's pretty big lighting load here, and I tweak that in the mechanical system. So there's other things that we're going to deal with next semester, artificial lighting, HVAC, that will take this to the next level. Um, you see what a big role that windows play. Let's see if I go back to something like this. Um, but only really once we get to high performance. When we're here at passive house level, then adjusting this becomes very important. The orange row, um, and we still have a lot of infiltration. Even with zero point 0.5, I noticed that their default, I think, is 0.1, um, which is possible, but that's pretty difficult to do. Um, anyway, I think that let's see. Yeah, maybe let's go back and look at a few more things over here. I'm going to just hit the edit button. Let's look at conditioning for a second, just so you realize. Um, no, let's not get into that right now. That's next semester. Okay, I think that's enough for you to get. Um, like I said, that's just laser blazing fast. Um, a lot of talking, a little bit of clicking. Um, you need to play with this yourself. But I want to show you. Now I want to go back and talk about. I think I'm not going to talk about now. I'm going to stop this video so that I have two separate videos. The next video I'm going to do right now is going to be about the full semester and how we've used Climate Studio, and it will end with a thermal analysis model like I just did here. But I'll be using a little bit more of a detailed design where we can apply all the different simulations that we've done so far. All right. I hope this helped. Um, Make sure you ask your professors questions. All right, bye.